Okay, here we go. What's our first step? We've got this projectile that's going upwards at a angle that we have no idea what is. They want us to try to solve this using the law of conservation of energy. So I'm just going to put theta right there. I'm not actually going to put an actual angle. And we know that the horizontal component is 30 meters per second. We know that the height is 20 meters. So what would y'all recommend we do? Okay, so we're gonna do LOL chart. All right, so we're gonna start off our system. We're gonna do L. We're gonna name our system, and we're gonna put L. So point, I think this first one is for point P, and the second one is, it didn't actually have a point listed to it, so we're just gonna write top instead for the distances between them. Okay, so we'll write our Cugus out down here. So we'll have Cugus, and then we'll have Cugus over here at the top. What is the system itself? Okay, so we're going to call it the mass Earth system. Okay. All right. At the very beginning, what do we have? How would we write this out? Yes. Okay. Well, that's not helpful, but okay. Do you have kinetic energy at the beginning? Okay. Do you have all kinetic energy at the beginning? You can say yes or no and both be right. It depends on how we want to do this. Where do we want the 0 point to be? If you set the 0 point right here horizontally across like this, then yeah, at the very beginning you can have quote unquote zero potential energy. If you're making the 0 point B down here, you've definitely got more potential energy at the very beginning. So it depends on how y'all want to work this out. If you consider this top point at point P the 0 point, you're going to have some negative values because some energy is going to go downward. Okay, so if you're just dealing with point P in the top, we can make this the 0 point, and we're not ever going to dip below that point. So I think we can be okay with it if you guys want to just go with point P in the top. Which would y'all prefer? Okay, so at point P, all of the energy is going to be kinetic energy, right? And then on the other side, when it reaches the top, how much kinetic energy does it have left? It still has some because it's moving in the right direction, correct? It has less, but you've also stored some potential energy, right? Okay, so we do have some stored, and I'm glad that y'all guys noted that the kinetic energy is still there. There is still a little bit of kinetic energy inside this object, and whereas we may not know exactly what that number is, we could probably pretty easily find it without too big of a deal. So let's see what all we know and what all we need to find. So, what is the equation for kinetic energy? Okay, so we have 1/2 m, and I'm going to call this VI squared. Is that okay? And we don't have any UG, and we don't have any US. We don't have any gravitational potential energy, and we don't have any spring potential energy. On the other side, we have kinetic energy. So what do we want to call that? 1/2. Okay, well, if we're going to go ahead and plug in numbers, we know the mass is 0.5 as well, right? So let's do 1/2 0.530 squared. And now what about our UG, gravitational potential energy? MGH. Okay, so the mass is zero point 0.5. G, acceleration due to gravity on Earth, is 10 meters per second squared. And then the H, the height is, I think it said 20 meters, right? Okay. So we know that these two are equal to each other because of the law of conservation of energy. There's no friction that's like losing this energy or anything like that. And it looks like we have everything except for m on the left side and vi squared. But that m is really just zero point 0.5, right? So I can erase that and I can make this 0.5. And then I think from there we just need to solve a little bit of the problems and then we'll be good to go. So yeah, don't have a calculator? Here, I got you one. Mm-hmm. Anybody else need a calculator? Your cell phones probably aren't super good at this. I mean, does it work? Yes, but you could probably just get yourself a $5 Walmart calculator and it'll do a better job. Unless you're just really stupid good at your phone. Let's see here. Um, yeah, everybody brought mass to the party. So I'm going to go ahead and just get rid of those 0.5s. So that's 1/2 vi squared is equal to half of 30 squared plus, see, 10 times 20 I think is 200. So that's 200 joules. Let's see, half of 30 squared. This is where I get really bad at arithmetic, so half of 30 squared is 450. Plus 200 makes 650. So that's 650 is equal to half of vi squared. So we're going to double both sides. 650 times 2 comes out to be, I think, 1300. Okay, so vi squared is going to equal the square root of 1300. Get rid of that square. Square both sides. So our initial velocity is going to be the square root of 1300, which if I can actually find the square root button in the calculator, 36 meters per second. Okay, 36.0, 36.1, 36 point. Okay, so if it's 36.05, let's say 36.1 meters per second. Okay, that's part A. So we can find the initial velocity of the object by using the conservation of energy, even if we didn't know what the angle was. And now that we know what the horizontal and the vertical component are, we could actually find the angle of the launch as well. We know that the horizontal component of the velocity was 30 meters per second. Now we know that the initial velocity in total was 36.1 meters per second. So we could find the vertical component of that velocity. Wait, wasn't that what we were looking for to start with? Okay, we're not done yet then, because what we just found was we found that, yeah, well, we're still not even done with part A yet, because this total initial velocity at the very beginning was 36.1 meters per second. That means that if we're going this way at 36.1 meters per second, and we're going this way horizontally at 30 meters per second, we're looking for this vertical side right here. So we can use the Pythagorean theorem, absolutely. So we need to find out, let's call this, I'm going to call this Vy. Let's find this Vy. So 36.1 squared is equal to 30 squared plus Vy squared. Okay, this is 900. The other one I'm not quite so sure of. 36.1 squared is a number. Oh, duh, right? Yeah, we totally just did it. Yeah, 1300. So I'm going to put 1300 over here. Okay, so then our Vy squared is 13 minus 9, 400. Take the square root of that. We get that our Vy is equal to 20 meters per second. Right. Because you're looking at it like, oh crap, they gave no. It's 20 meters per second, but it also goes up 20 meters. Okay, which is kind of weird, but it's kind of interesting how that happens. Okay, so now we know what our y component of our velocity is. Takes 1 second to get there. Well, after what? Shouldn't it take 2 seconds to get there? I think it takes 2 seconds to get there because I know that you're thinking is 20 meters per second, and if it has to travel 20 meters, that it would take it 1 second to get there. But you got to remember that it's actually slowing down because acceleration due to gravity is negative 10 meters per second per second. So if you have a velocity of 20 meters per second, you're basically slowing down in speed 10 meters per second every second. So after 1 second, you'll be traveling positive 10 meters per second. After 2 seconds, you'll be traveling 0 meters per second. So the time that it would actually take to reach the top would actually be 2 seconds, not 1 second. Okay, but I don't even think that was a question. I think that was just me getting on a tangent. What was part B on this that we had to figure out? Okay, I'll go back and look it up. The work done by the gravitational force on the particle from P to B. So we want to go from work done by gravity. Okay, work done by gravity from P to B. That's going from here, point P, to B down here. It's going to the two blue dots. Okay, do what? Yeah, the big thing to consider here is, are we dealing with a positive work or are we dealing with a negative work? Okay, what is the direction of, because remember, whenever we deal with work, it's going to equal force times distance parallel, right? Or FD cosine theta. Uh, in this case, what direction is gravity pointing? Okay, so gravity is pointing this way, right? Okay, what direction is the displacement going? It's going up. We're starting here and we're ending up down here. Um, mm, so we're only dealing with, all right, so like, okay, that's a good point. So if it's going to the right, that doesn't make any sense because we're only dealing with the work done by gravity, which means that if you're moving to the right and gravity is pointing down, what is the difference in the angle between the force of gravity and the horizontal displacement? 90 degrees, right? What's the cosine of 90 degrees? 0. If you type in the cosine of 90 in the calculator, you get 0. So we're only really dealing with the vertical displacement. We're not dealing with the horizontal displacement. So you're right. Whenever I said displacement, I did not specify that it's really only the vertical displacement. So I'm sorry about that. So we're dealing with the vertical displacement. The vertical displacement goes down. What is the angle between the vertical displacement and the force of gravity? 0. What is the cosine of 0? Okay, so this is going to be a positive number. This is not going to be a negative number. So we're going down. We're going to have a positive number for the work done by gravity because it is working in the direction of the force that is being applied. Right, we know the distance is 60 meters. And we know that the force is the weight of the object. So the force in this case is just going to be mg because it's the weight of the object. Yeah, it is the gravitational potential energy. So for part B, and like for example, this part up here, uh, you are going to be getting a negative value up to 20 meters, but then you're going to lose it all. So it's going to go like negative 20, then 0, and then positive whatever this value is over here. Okay, so we have a, uh, let's see, mg is 0.5 kilograms times 10 meters per second squared times 60 meters. Half of 60 is 30. 30 times 10 is 300. So it looks like our work done by gravity is 300 joules. Does everybody agree? Okay. That one looks a little bit harder than it actually is. And then let's see here. For part C, the horizontal and vertical components of the velocity vector when the particle reaches B. Okay, so we're looking for, I'm going to go ahead and I'm just going to go down and write a part C. So C, horizontal and vertical vectors at point B. Okay, so I'm going to go ahead and just draw a quick recap of what we did. We start here, we end here, and there's a lot of information that we already know that's written up on the spaces above. So we don't have to write them all down because I don't think they're all going to be super handy, but there's a couple of different pieces of information that we can use. And there's a couple of different ways to solve this. They want us to specifically worry about conservation of energy. So we know that going down here, that 300 joules have been used. But how do y'all want to go about this? I know down here at the bottom, if I were to draw the velocity at the very bottom, what direction would it be going? It's going to go like this. Shouldn't work like this, right? Is it going to go like this? Okay, so it's going to be going kind of like diagonally, right? It's going to go in like, yeah, this is going to be our VF. It's going to be the direction that it's traveling as it goes down. This is like right before it hits the ground, which means that we have two components for our velocity. We can break it down into a horizontal and we can break it down into a vertical component. So we know already one of these. Okay, so we know that the work done by gravity, so UG is equal to 300 joules from P to B, right? So I'm going to go ahead and write P to B up there as well too. But I already know one of these speeds. I'm not completely lost on the speeds. I already know one of them. Which one do I already know? Which one? Give it a fancy name. Horizontal. We know the horizontal velocity already because it doesn't change. So if it starts off at a value of 30, it's going to end up with a value of 30 meters per second. Okay? We do not know the vertical, and we do not know the diagonal one as well. It's not the same as what we started with because it's dropped some distance. So it's going to be going faster than 36.1 meters per second. It has to be going faster than 36.1 meters per second. So let's use some Kugis to see what we can come up with, or some kind of conservation of energy. Okay. Let's make our LOL chart. I think. Well, I mean, we may not even have to use an LOL chart, but yeah, you already have it up there. Um, we can use those pieces of information to go ahead and give us answers about what we're doing now. So I'm looking for ideas. Looking for ideas. At the very bottom, isn't this all going to be kind of kinetic energy? Okay, so at the very end, this VF is going to have a kinetic energy of 1/2 m VF squared. But where did all of that energy come from? Gravity, right? Okay. How much work was done by gravity? We had 300 joules of energy done by gravity, correct? Man, if there was only something that related kinetic energy and work done. If only we had some way or some method to the work, what was that? The work energy theorem? Oh man, we hadn't done that one in like a month. Okay, okay. You got my attention. There's a work energy theorem. What does that mean? Look it up. Look it up. All I gotta say is look it up. What's the work energy theorem tell us? There is a tool in the tool belt. This is like you know that the screwdriver is there. You just got to go find it. The screwdriver and the work energy theorem are both tools. It's just that one of them is a math tool and the other one is a delta K. All right, delta K is equal to what? Okay, anytime you have a change in kinetic energy, that's equal to the amount of work done. Okay, so in this case, we know that the total amount of work done from point P to point B is 300 joules. It was all the gravitational energy that was spent, right? And we know that that's going to equal the change in kinetic energy. Well, the good news is we know what the kinetic energy is at the beginning. So it's Kf minus Ki, or the initial minus the final minus the initial. But we can find the initial kinetic energy. I think we may have already found the initial kinetic energy. If not, we've got this velocity up here of 36.1 meters per second, so we can pretty easily find that. The initial kinetic energy is 1 half 0.5 times 36.1 squared. The final kinetic energy is 1 half 0.5 times whatever the heck the VF is squared. And that's going to be equal to 300 joules of energy that got spent in this process, the work done by gravity, because gravity did 300 joules of work. Okay? So we need to get a number for this 1 half 0.5, 36.1 squared. I need to get a number for that in joules. So 300 joules equals this number minus this number over here. It's not good? What do you mean it's not good? Okay. 325 joules. We'll write down. It's okay. Point 0.8. All right, we'll add the point 0.8. 325.8 joules. All right, that's fair. On the other side, well, we can't really figure out what this one is. So that's 1 half times 0.5 VF squared. Let's add 325.85 to both sides. So that makes this 625.85 joules equals 1 half 0.5 VF squared. Do what? Oh, I wrote 5 in joules at the same time. Yeah, sorry. 625.8 joules. You're right. 625.8 joules equals 1 half times 0.5 times VF squared. We're going to multiply by 2 twice because that's a 1 half and a 0.5. So we're just going to do times 2 times 2, or just multiply it by 4. 625.8 multiplied by 4. That's 2503. So I get about 2,503 joules is equal to VF squared. So our final velocity at the end is going to be equal to the square root of that number. And I don't know about y'all. Okay, yeah, I get about 50 as well too. 50 meters per second. Okay, and that would be our final velocity going down this way. So this would be 50 meters per second. You do have to find the vertical component of it. You can do just the Pythagorean theorem. You could also recognize that this is a 3 blank 5 triangle. This is a 3, 4, 5, so you could kind of cheat and say that this is 40 meters per second. Because these are multiples of 10. So, if one of the sides is 3, one of the sides is 4, then the hypotenuse is 5. That shows up on the ACT a lot of the time. But this is really just 3 times 10. So 3 times 10 and 4 times 10 is going to give you a hypotenuse of 5 times 10. You could do the Pythagorean theorem and you'll get the same answer. You'll get about 40. Okay? So that means that this problem actually worked out a little bit easier than I thought it was going to. Relatively, like easy is relative, right? I mean, this is an AP Physics problem, so okay. Brain hurt. We got 10 minutes. All right, so let's see if we can kind of get you guys started on one more, and we may have to pick it up to finish tomorrow. Did I do the? I don't think I've done the Atwood machine one with you guys yet. Oh, but now we're gonna do it with energy though. This one's not this. We're not gonna solve the Atwood machine with forces. We're gonna solve the Atwood machine with energy. So let's write out an Atwood machine. So we got a little bit of time left. So let's just draw it out. You got the axle or the pulley, and then you've got a mass on one side, and then you got a mass on the other side. One of these masses is on the ground, and it's the one on the left side. If it was the one on the right side, y'all might get a little bit worried about me. There you go. There is a distance that goes this way. This height is 4 meters. There are two masses. One of them is 3 kilograms. The other one is 5 kilograms. So this guy down here on the bottom is 3 kilograms. This one on the very top, this is 5 kilograms. And let's see here. What I do? What? The Right, the 5 is the high one, but it hasn't been released yet. Yeah. So what's going to happen is you're going to let this go and it's going to fall. And that's what we're going to need to find out. So for part A, what we're going to need to find out is the speed of the 3 kilogram mass right before or right when the 5 kilogram mass hits the ground. That's what we're looking for starters. So, yeah, let's start with that. Kind of think about it for a little bit. The speed of the 3 kilogram mass right when the 5 kilogram mass hits the ground. Good. Okay. So like since they're connected by a string, the speed of the 5 kilogram block and the speed of the 3 kilogram block are kind of locked in place with each other. So the speeds aren't going to be different. Like one of them is not going to be 20 meters per second and the other one's going to be 30. That doesn't make any sense because then the string would have to like stretch out. So all we have to do is find the speed of the 5 kilogram mass first, and then from that speed of the 5 kilogram mass, we can find the speed of the 3 kilogram mass. They're going to be the same. Okay, so this is kind of a trick question in that sense. And we are supposed to try to figure this out with energy, not with forces. Because I know that we've done it before with forces by finding the acceleration and then using the kinematic equations. But let's not do it that way. Let's do it with energy. So let's try to come up with a way to try to find out how to do this with energy instead. Ideas? Instant Kuggas. All right. So LOL chart, right? All right. That's fair. When it's energy, you can never go wrong with an LOL chart. You're absolutely right. So we're gonna write our Kuggas out. Okay. All right. Um, at the very beginning, do you have kinetic energy? No. Do you have potential energy? Yeah. It does exist. Okay. Do you have spring potential energy? Okay, good. Um, at the very end, you have kinetic energy right before it hits the ground. Okay. Do you have potential energy? Well, okay. What is your system here? Mass pulley? What's causing the energy to be gained and lost? The pulley is not causing the mass to be gained and lost, or the energy to be gained and lost. Gravity. So this is a mass Earth system. Okay. I know the pulley is there to kind of mess us up a little bit, but this energy transfer is being transferred through the force of gravity. The pulley does not supply a force. The pulley does not supply a force. So therefore, whenever it comes to analyzing it in the system, it's not really a method of force transfer unless we want to make it that way. And then we're going to have to start dealing with some really complicated stuff. We're going to assume that this pulley is frictionless and massless so that we don't actually transfer energy through the pulley. If you write pulley, you're going to make your life a lot more complicated because then you're actually going to have to think about the pulley and what the pulley does. So you're including both masses, right? Okay, if you draw a situation of what the Atwood machine looks like afterwards, you're going to find out something though. We're going to find out that this chart has something weird to go along with it because we didn't. I don't think y'all included everything at the very beginning, um, because at the end, this 5 kilogram mass is going to be going down here, and this 3 kilogram mass is going to be up here. It can't all be kinetic energy because this has been lifted off the ground, so there has to still be some potential energy left over because this 3 kilogram mass is actually lifted up, right? Okay, we're all in agreement with that? It's okay? It's not going to hurt us? All right, what is the formula for UG on the left side? Okay, so do we have those numbers? 5 times 4 times 10, right? So, because this is the 5 kilogram mass times 4 meters times 10, 8? What? No, don't use 8 this time because it's just the only energy is coming from this 5 kilogram mass. So it'd be 5 times 4 times 10 mgh. That's going to be 400 times 5. Is that 2,000? I'm not very good at this. How about, let me try again. 40 times 5. Is that 200? There we go. So we got 200 joules on the left side. On the right side, we've got 1/2. Now the mass, well, the only one that's like got kinetic energy that goes along with it is the 5 kilogram mass, right? Wrong. They're all moving, right? Yeah, so like the 5 kilogram mass is moving and the 3 kilogram mass is moving. So they both add together. There's two different speeds there. So can we combine them together into one kinematic or do we have to, or sorry, one kinetic energy or do we have to add them separately? So 1/2 5 times v squared plus 1/2 3 times v squared. I think we could have actually added them together and been okay because all of these are shared. The 1/2 is shared, the v squared is shared. So that's really like 1/2 5 plus 3. Do what? They have the same velocities because they're connected by a string. So we could take that 5 plus 3 and we could add it together and just make 8. I think that's okay. And then I think that's fine because I think a lot of people look at that and they're like, yeah, no thanks. I see 2v squared. That's not my friend. And then the last part is mgh, but that's only the 3 kilogram block. So that's the mass of 3 times gravity, 10 times the height. Well, if the first one went down 4, then this one's going to go up 4. So that's 3 times 10 times 4. That's 30 times 4. at 120. Okay, I'm going to go ahead and say 1/2 8 times v squared equals 200. All right, we're almost done, I think, but we're almost out of time too. So let's really try to finish this out. 200 minus 120 is 80. Let's see. It looks like I can divide both sides by 8. So that gives me 10 is equal to 1/2 v squared. So it looks like my velocity is equal to the square root of 20 meters per second. So that's how we would actually figure it out using energy and not using the kinematic equations and Newton's second law. And I think we're going to have to stop it there because I think we're almost, yep, there it goes. We're almost out of time. So have fun. Talk to you guys tomorrow.